Okay, so thank you. So I'm Michael Brown from York University. I'm also at Samsung at the moment. And this is really work by my student, Mahmoud Afifi. And I really regret that Mahmoud couldn't come. So he had some family issues, so I had to go take care of that. So I'll be presenting his work. Let me just talk about taking a photo first. So when you take a photo on your camera, there's actually quite a few processing steps that take place that transform the raw sensor image into the sRGB image. So what I'm going to talk about today is the white balance procedure. So one of the crucial steps that we apply is white balance. And white balance is basically computational color constancy. That's what we call it in computer vision. So for a human, if you look at a piece of paper, if you look at it indoors or outdoors, it always looks white to you. So you have this built-in color constancy, but the cameras don't have this. So for the cameras, you have to do it in computation. So this is essentially white balance. And so you've kind of seen these type of images before where we can see the different color casts. And essentially what we're trying to do with white balance is remove the color cast due to the illumination. So the challenge is if I give you an image, you have to estimate what the illumination appearance is to the sensor. And so if I give you this image, what you're trying to do is you're trying to estimate from a single image what is the sensor's response to the illumination. And this is just an RGB vector, okay? And then once you have this RGB vector, you just divide it out. So this is the white balance procedure. So this is easier said than done. So that was magic, but usually we have some lumen estimation algorithm. And so this is essentially your camera's auto white balance. So you can set it manually, but usually we use auto white balance. And you can see it's a challenging problem because I could give you an arbitrary image and you have to estimate what the illumination is. It could be all trees and grass and you still have to figure out what the illumination is. So I want to make it clear that this happens early in your camera pipeline. So this happens on your raw sensor, and this is going to be important because you're going to see later this is the whole point of our paper. So there's really two approaches we take in the literature. So the older approaches are what we call sensor-independent or statistical methods. They look at something related to the color distribution and they try to estimate out the illumination. And so you've probably heard things like gray world or white patch. Of course, now we've moved into the modern era, so we use deep learning or we use learning-based methods. I want to remind all the younger students there was stuff before deep learning. So we had Bayesian methods and things, but of course that's all been crushed by deep networks. So now everything learning-based method is some type of deep network. And here's the interesting thing about it. So if I have a camera, I just get lots of examples of images. I label the images, what's the ground truth illumination, and then I train a network to learn this. But the interesting thing is you have to do this per camera or per sensor. Okay, so if I have a new sensor, I have to retrain that network for that sensor. Why is that? Because the different camera sensors have different spectral sensitivity. So the raw RGB space is not standard. It's unique to each sensor. So you can train it for this sensor. This is a Nikon or a Canon. And then when you move to a different sensor, you have to retrain it. So that was the whole point of this paper. So this is what Mahmoud was working on. And he tried to come up with a sensor-independent framework. So the idea was to have a two-step network. So the first network is going to learn a mapping function that maps your raw image into some working space. And then from this working space, we do the illumination estimation. So I'll go through this. So the idea would be you give me a raw image from any sensor. And what we're going to work with isn't the actual image itself or the spatial information. We just derive the color information. So the illumination estimation really shouldn't matter what the scene content is. So we use this representation that's really the color histogram in 3D just projected onto an image. Then we run a network that learns a 3x3 transform that is applied to the image, and it changes all the colors of your original raw RGB into some new mapped image or what we call the working space. Now in this mapped image, we again extract out just the RGB histogram, and then we run it through an illumination estimation network. And interestingly, these architectures are virtually identical, and then it outputs the mapped illumination. Now this mapped illumination is in the map space, so when you want to apply it, you just apply the inverse matrix, and then you white balance your image. So the starting point is this RGB projection. This is actually based on some prior work from Google. So this is John Barron's work a couple years ago. Mahmoud had modified it slightly for a paper this year at CVPR. And in his procedure here, he actually learns how to bend the image, so how many bends that you need, and he also learns, I think, a smoothing factor. So you need to look at the paper for the details, but essentially, we take the image and we convert it into this RGB UV histogram. And then we just simply run that through this network, and then it outputs a vector of 9 numbers, and then we reorder that into a matrix. And then we check to see if it's invertible, and if it's not, we just add a small perturbation to make sure this is an invertible matrix. Okay? Then you take your mapped image. We again extract a new histogram from this mapped image, and then we learn this network that predicts the illumination. The loss function is just simply the angular error. So when we do this, this is standard for all illumin estimation networks. We just use this angular error, so you're really just interested in the direction of the illumination. So you could think of the ground truth. This is just a vector in RGB. I'm going to show you how we get ground truth in a second. And then you just take your estimate and you just look to see how far away you are in terms of angular error. Okay, and so here I'm showing you the loss function. And so what we do is we just train the whole thing end to end by just back propagating this loss function, the angular error. And how we get the ground truth is all of these images have a color chart in them. The color chart has a series of achromatic white patches, and we just use one of the white patches. Different data sets calculate this differently, but it's all based on the same principle. There's some white reflectance, and that's your ground truth. Okay, so that's how we get our angular error. So I'm just going to run you through how this would work at test time. So the interesting thing is it's not just sensor dependent or sensor independent, but this mapping isn't just based on the sensor, it's actually based on the image as well. So if you give me an image from some sensor, some camera, I'm going to extract this RGB histogram. I'm going to run it through my network, and it's going to predict a matrix. I'm going to take this matrix, apply it against my image. Now I'm in my working space. I again extract this histogram, and then I estimate the illumination. And then I apply the inverse, and I get my corrected image. And if you had another image, you would go through the same procedure, but you would get different numbers out, right? This would be related to the sensor and the input of the image. And you again map to the working space, extract another histogram, and then run it through your illumination estimation network, and then apply this. So we tested this on several data sets. So there's 3 major data sets. There's the NUS8, the Gaylor-Schur, and the Cube data set. And the way Mahmoud did this was he would train the whole network and leave one of the cameras out, and then test on that camera. So that means the network hasn't even been trained on that particular camera. And these are the results that he gets. Now, I don't have enough space on my slides to show you all the methods he compared against, so I'm just highlighting the more recent ones. But this average, let me use my mouse here. Oh, there. This sensor-independent methods, these are the older methods. These are the statistical-based methods. And so we can see that the sensor-dependent methods, which are all the learning-based methods, you can see they do quite well. They beat the statistical methods. And you can see we perform quite well. So on the NUS8 data set, we actually do really well. But on some of the other data sets, we're not the best. We can't beat the sensor-dependent methods. That means it was trained just for that sensor, but we're very close. And so this is on the NUS8, this is on Gaylor-Schur, and this is on the Cube data set. And the Cube data set, they have 2. They have the Cube, and then he added some more images on the Cube Plus. So here's another example. This is some results. So this is showing you the input RGB. So little caveat here, you can't really display a raw image, right? Because this is not really in a displayed type of color space, so we just show it here. But what we've done is this is the mapped color space. And this, we've ran it through the rest of the pipeline after we've corrected it. So this is what our corrected image looks like. And this is what the ground truth if you use the actual illumination from the color chart. So not bad. So that's it. It's a nice and simple paper. So presented a method that basically attempts to remove the relationship or the reliance on the raw input. So we have a sensor-independent illumination estimation. The results aren't as good as if you trained each sensor, but we only have to have one network. And it generalizes to cameras that you haven't seen. Okay? And that's it for me. Thank you. Questions?
I had a question regarding, so the matrix and 9 numbers, they're trying to, in a sense, make the image sensor independent, right?
You can think of those 9 numbers are trying to map. So the 9 numbers are applied to each RGB. So it's just a color mapping, a 3x3 mapping that brings all the raw images into the same space.
Into the same space. So did he observe that given the same scene with 2 different sensors, after applying that matrix, were those 2 mapped images the same?
Yeah, so he has. So I have this slide that I didn't put in here because I thought it was too confusing.
Yeah,
but it's somewhat like what you're asking. So this is showing you in what we call a chromaticity space. Okay. So these are the different sensors. There's 3 sensors, and this is kind of what the space looks like after you apply the mapping. So it does bring it into a new space.
Yeah.
The reason I didn't like to show this image is for people who work in illumination estimation, it's pretty easy for us to see that these are the different, usually this would be like a red light and this would be a blue light. This kind of mixes it together, so it kind of lies more along a line, but it does bring everything together. Okay. In some of the data sets, like the NUS8 data set, they actually have the same scene, same illumination, multiple cameras. But the other data sets, the different cameras have different scenes, so you really can't do that comparison. Yeah.
One is, if you just go back to that diagram, so the image mapping matrix that's predicted, for a given sensor, regardless of the image, that matrix should be the same every time? Yeah,
I agree with you in principle, that should be right, but I think in general that a single 3x3 is not enough to map all the images, so in my mind, this is the beauty of deep networks, we can just map whatever we want on them, so pretend that it does this. I agree with you in principle, but he is doing this per image. So you could think of it as a local fit for that image for the particular colors in that image. But I agree with you. You could think of a way to just calibrate all the images, like use the color chart and just map to a canonical space.
I mean, I was kind of wondering how consistent is that matrix if we've given one sensor and multiple images.
Right, yeah, I agree. I haven't seen those experiments, but I agree with you in principle, that's right, yes.
And the other question, I was wondering if, because you apply the image mapping matrix to the image to make a new one and then build a histogram.
Yeah.
Can't you just
I also agree with that, totally. Yeah. So that's I'll pass that on to Mahmoud. That's the beauty of giving the talk for your student who told me he was going to come and didn't come. So I can, I'll ask that as thesis defense. But yeah. Thank you. Thank you.
Are there questions from the other room?
No, there are no questions.
Thank you for the talk. I think that more than just one factor affect the matrix M. For example, the exposure and the content, and also the light. So, do you have any idea, or have you done any informal experiment on how these affect the values of N, and also the estimation result, the last 3 numbers?
Yeah, I agree with you. I think later when you do the projection onto the RGB UV, usually the things like the scale of the exposure disappears. So I agree with you. I think one thing is for these data sets like the NUS8, the exposure is pretty clean across the images. So that may be a factor that we didn't deal with, that we just got lucky because the data sets have that. But I do kind of feel that even if there's an arbitrary scale in this, it's going to drop out when you do the projection onto the YUV plane. That's my guess, but I understand what you're saying.
So are you saying that it would be better to find some way to normalize M at the end?
Yeah, or you could probably just normalize it already. You wouldn't, you could just take M and normalize it to some scale factor.
I see. Thank you.
Yep.
Okay, any more questions from both rooms?
Is it another question? Same, okay.
About the invertible matrix, so you mentioned that if it's not invertible, you add a small perturbation, and then it becomes invertible. But at that point, isn't it going to produce almost like a really bad image because there's...
Yeah, I agree with you once again. I think it was a rather large perturbation, not a small perturbation. So actually, if you look at this, when he maps back, so I'll pass that information on. But when he maps back, when he inverses, you can see it's not exactly the same as the starting point, and I'm pretty sure that's due to those perturbations. That's sort of, so I don't think he found that he needed that very much. I guess I can say, because he's not here, I was surprised it worked, because I was really, I was really worried that that matrix would be a bad form. And I was quite surprised that he didn't have to do too many tricks to get this to work. But I agree with you. If that matrix comes out quite awful, it's just going to ruin everything. But I think, in a way, I guess because then the rest of the network wouldn't work well, so the back propagation takes care of this. So let's pretend that the network takes care of it.
Fair enough.
Call it that. All right. Yes, yeah, I agree. No more questions, yes. And I believe Mahmoud's email is on the paper, so you can feel free to mail him, yes.
Those discussions are interesting. And
Okay.
next speaker, we'll move on to the next talk. Yeah, the next talk is robust synthesis of adversarial visual examples using a deep image wire from the University of Surrey.
Where's my lead? Oh, let's use this one. That'll work. Let's plug that in. Right. Hang on. Lovely. Hi, so I'm Tommy Gittings from the University of Surrey, and I'll be talking to you about how we can robustly synthesize adversarial examples with a deep image prior. So here we have a picture of a cat, and we're pushing it through a CNN classifier, which manages to recognize that it is indeed a cat. So then to that we add some innocuous-looking noise and get another picture of a cat that looks essentially identical, but then we push that through a CNN classifier, and that's a clothes iron. So what's happened here? Well, this is an adversarial example, and so we've just targeted this noise specifically to do exactly that. So I don't think I need to explain why this is a problem or why this is interesting. So here's some more examples of that. So these two examples here are both targeting the class Wallaby. So the one on the left, that has a bigger perturbation applied to it. The one on the right has a smaller perturbation. So the idea of this being that this bigger one, this would be more resilient to any kind of transformation you could apply to it. And so these are targeted attacks. So we picked what class we wanted to target. We don't have to do that. We can also just say we want it to not be the correct class. And in this case, we applied a small perturbation across the whole image. There is another way we can do this that we'll talk about later, where we apply a large perturbation and we only apply it to a small region of the image. So now I'll explain how other people have been producing these examples. So we just start with this picture of a cat up there, and then we push it through our classifier, get out our vector of probabilities, and we take the cross-entropy loss with this one hot vector of the target class, which was in this case clothes iron, and then we can just apply back propagation right into the original image, into its pixels, fixing the weights in the classifier, and then we just perform a gradient descent like this with a number of steps, and we're bounded in this small ball by epsilon, and that stops our perturbation getting too large. Now we can make epsilon large, which will give us this image on the left, or we can make it small, which, as I said, that trades off robustness for imperceptibility. So what is our contribution? Now, here you can see this Carlini and Wagner method. That's a similar method to FGSM, subtly different, but that image that was classified as a wallaby when it hadn't been rotated, but then we applied a small rotation to it, and then it became an ice cream again. So this is what we're trying to avoid with our method. So this happens because the perturbations that are produced by these methods, they're very small, they're very high frequency. So what we want is we're going to frame this as a reconstruction problem, and we're going to regularize it using something called a deep image prior, and this will promote perturbations that are lower frequency, and they can be slightly larger while still not being visible. So what is a deep image prior? Well, the idea of this is that a convolutional neural network encodes some information about how natural images look in a similar way to a total variation prior, but in it slightly more subtly. And
So this is supposed to give you an idea of what sort of thing it's doing. So you can see no prior, you get a very grainy looking image, a total variation slightly better, and a deep image prior even better still. So this is what it was applied to in the original paper. This is super resolution. They also did things such as in-painting, various other reconstruction tasks. So all this is using is the structure of the network. That's going to be your prior. And this allows you to produce lower frequency details while still looking natural. So here's our method. It's based on these methods, Carlini and Wagner, and LBFGS. Now, they are similar to the FGSM in that they backpropagate into the original image, but instead of bounding in an epsilon ball, they use this two-term loss function. So they have this reconstruction term here that's just the norm of the perturbation, and then another term that is just your cross-entropy loss of the classifier, and then this little weight here, D, which balances the two. So instead of doing that, we're using the deep image prior idea, and we've attached this special network here, this encoder-decoder, and instead of perturbing the pixels of the image directly, we are going to change the weights of this network. So for every single image, this network gets initialized from scratch randomly, and then we overfit on this one image. So every image gets its very own network that we train up to produce our adversarial image. So yeah, the idea being that this just provides some form of regularization. So that's our loss function, which is exactly the same, apart from the fact that we're looking at the output of this generator network rather than just the image directly. So here's an example of what this looks like. So you can see the original on the left, then ours in the middle, and this large perturbation of the fast gradient method on the right. So these two, they both have very similar resistance, robustness under the affine transformations, but as you can see, ours is a lot less noisy, and it looks a lot closer to the original image. So this is what the perturbations look like if you magnify them up so you can see where they're localized across the image. So the majority of the methods, they spread the perturbations out relatively evenly across the image, with the exception of this method, which, as we'll see later, just doesn't work very well. So whereas our method, it localizes the perturbations it sort of hides them in the high frequency details of the image. It almost smooths it out slightly in an imperceptible way. So it looks very, very different to what's happening with the other methods. So we've evaluated our robustness. We tested on 2 classifiers, a VGG and an inception. We used 1,000 ImageNet images to test, 10 target classes, some small rotations. These are very small rotations, which is enough to break most of the methods, and also some very small scalings. And we'll be looking at the success rate, which is you take the images that you originally got right, and then you look at how many of those do you now get wrong, divided by the number that you got right originally. So this is what it looks like. So the orange line is that big FGSM method that looked nasty, horrible, lots of high frequency noise, very visible. And then our method is the blue line, which achieves a similar robustness under the transformations to FGSM, but it's a lot less visible. And then, as you can see, the other methods, they do a lot less well. So this sad-looking purple line at the bottom, that was the one that had just a few pixels it perturbed across the image. Yeah. Okay. So we did a perceptibility study using Mechanical Turk, and from this you can see that for the most part ours was equally imperceptible to the other methods, with a couple of exceptions, and it was definitely less perceptible than this large FGSM method. And so we also tested for time, and ours, as you would expect, is slightly slower, but for the state-of-the-art methods, which are really this one, it's not not horribly dissimilar. It's not sort of an order of magnitude slower or anything. Now, there's this other type of adversarial attack that I alluded to earlier, which is an adversarial patch. So these were invented by Brown et al. And the idea of this is that you can just perturb this small region of the image, but the idea is we can apply this to any image. So I can create this patch. It will work on top of any image, at any location, at any size, and with any sort of rotation you want to apply. So the idea being you could print this out and stick it in the real world, in principle. So the way they train this, they're just perturbing the pixels of the patch, analogously to how we just perturbed the pixels of the image before. So this guy here, A, all this is saying is you take the patch P, apply it to the image X at location L, and with affine transformation T, so your rotation and your scaling. So, and then they're just averaging over all of the images in your training set, all of the transformations we're interested in, and all of the possible locations in the image. And then that, we hope, it creates a patch that you can apply wherever you like on any image, maybe even print it out, and it will work. So that was their results there. So then we've adapted this method to produce our own adversarial patches, and so again we've made effectively the same change. So this is the same encoder-decoder network as before. We just put that there instead of the patch. But other than that, it's the same. We're averaging over this whole test set of training set of 1,000 images in different locations, different transformations. So our aim was for our method to be faster while achieving the same performance. And so this is what they look like. On the left you have Brown's method. On the right you have ours. So they do look quite different. I don't know. These are supposed to be targeting toaster. So I don't know if you can see a toaster in there. Maybe ours looks more like a toaster. I'm not really sure. So these are the results. As you can see, ours look very similar. They've effectively performed the same, but ours took only 11 minutes to produce a patch, whereas theirs took 277 minutes, which is over 4 hours. So to conclude, we produced adversarial examples using a reconstruction approach and a deep image prior, which achieved better robustness to the affine transformations than state-of-the-art methods, but we were equally imperceptible, and we could apply the same method to produce adversarial patches that match the performance of the current method, Brown et al., while being much faster to produce. So I've left you with a few examples of the output of our method there. My email's at the bottom. Does anyone have any questions?
Okay, time for questions? Yeah.
Have you done, thank you for the talk. Have you done an experiment to video sequences? So let's say if you apply the method to a video sequence, can the users see any trace of modification?
No, I haven't looked at video at all, no.
Oh, okay. Thanks.
I love papers that break vision systems. It's nice that we can have them. So one thing I noticed is that the robustness you had to rotation and scale was over relatively small numbers. I'm wondering if you could kind of, if there would be any merit, say, in extending the system so that you generated an image, then rotated and scaled by large amounts and made sure that all of those generated images were adversaries. Could you make this substantially more robust and adversarial?
I mean, yes, you could do that, and I'm sure this would work. But the larger you want the sort of acceptable size of rotation or scale to be, the bigger your perturbation will have to be. So at that point, your perturbation is perhaps going to become visible, and then you may as well be using a patch, and the patches do have resistance to much larger rotations and much bigger differences in size.
Okay, thanks.
Yeah, any questions from the other room?
No, there are none.
So, hi. Got a quick question to check my understanding. So, it seems like you backpropagate from the target class.
Yeah.
And does that require you to know the exact weights of the classifier you're trying to attack, or so how does this work?
Yeah. Yes, this does. Yeah.
Okay.
So you have to be able to backpropagate through it. So you need to know what it is as a differentiable function, essentially. So if you're sort of trying to get at, could you attack a classifier that you only had as a black box? So you have an input and an output. And there are ways you could go about doing that. I think what you would have to do is pick sort of an ensemble of common classifiers and try and create an example that will fool all of them, and then hope that the classifier you're attacking has a comparable architecture to those that will then be fooled by this example. That's sort of using this kind of method, that's really the only way of going about doing that, I think.
Okay, thanks.
Okay, if we have no more questions, we'll move on to the next talk. Thanks, speaker, again. The third talk in the session is towards weakly supervised semantic segmentation in 3D graph structured point clouds of wild things. It will be City University of New York.
Okay. My presentation is towards weakly supervised semantic segmentation in 3D graph structured point clouds of wild things. And this work is jointly finished by the University of New York and the University of Leicester. So for my presentation, I will talk about 5 points. And the first section is the motivation of our research. And the second part is going to be our approach. And the third part, I'm going to show some experiment result. And the fourth part is the conclusion. And the final section is the question. Okay, let's first go to the motivation of our research. Let's have an example of the 3D point cloud segmentation. Our main task is to do the segmentation, and we have an example of the indoor scenes with n points, and each point has its X, Y, Z information and also the RGB information. And what we need to do is to predict the level for each point. And then we're going to got n levels to generate the segmentation result. And we have another 2 examples of the indoor scenes. And as we can see, it is obvious a large scale of million points, and also because of the variations of scenarios and objects. And all those facts can lead to this problem to be very complicated. So for the existing approach, it is mainly the supervised method. So we have 2 examples. Both paper was published in 2017 in CVPR. The first example is directly input the 3D point cloud, and via the here the example is use the point net, use the encoder and decoder. We directly output the segmentation result. And the second method is first to voxelize the 3D point cloud, and via 3D CNN we get the voxelized segmentation result. But both these 2 method has its own problems. The first one, it's going to require the 3D annotations, and as we know, it's very difficult to annotate all those points. And the second method leads to the problem of the low representation accuracy and high redundancy because of the inner. It requires the inner structure, but which is actually not helpful for our segmentation. So let's go to our method. Our motivation is to use the 2D signal for the supervision because, as we know, it's much easier to obtain the 2D signal than the 3D ground truth. So before we go through the our method, let's first look at the usual structure of using the 3D ground truth. Here is the example of the 3D point cloud data. And via the encoder and decoder, we get the prediction result. Suppose we have the 3D ground truth, and then we're going to calculate the loss between the ground truth and the prediction result. But if we do not have the 3D ground truth, how to do the 3D point cloud segmentation task? So here we suppose we're going to have different RGB images from different viewpoints, and it's related to the segmentation map. We're going to combine those 2D segmentation map as the ground truth. And in our work, we're going to calculate the loss between the prediction result and the 2D ground truth. And but the challenge with the 2D supervision we have mainly has 2 points. The first one is the points collision. And here we can say, when we try to project the 3D point cloud into the 2D plane, in some case, one point going to be projected to one pixel location. But in some case, multiple points going to be projected to the same pixel location. So how to solve this problem? And the second challenge is the object occlusion. As we can see from the image, here the wall is partially occluded by the computer and also by the bookshelf. So when we projected it into the 2D plane, they're going to have some intersections within the same area. So how to segmentate those points? Okay, let's go to our approach. So here is the whole structure of our research. It's mainly composed of 2 parts. The first part is the graph-based pyramid feature network. And the second part is the 2D optimization, which is used to optimize the whole pipeline. And the input is going to be the truncated point cloud and together with the 2D ground truth. Okay, let's go see how we solve this problem. And we're going to explain the truncated point cloud later in the dataset part. So we input the truncated point cloud and extracted both the high-level features and the low-level features to generate the segmentation result. And then we're going to project the segmentation result into the 2D plane. But as we know, we're going to meet 2 problems as we mentioned before. So we proposed use the perspective rendering and also the distance field to optimize the projection result. And then we're going to calculate the loss between the 2D ground truth and the optimized prediction result. Okay, let's look at what is the perspective rendering. As I explained, in some case, multiple points gonna be projected into the same pixel location. So how do we solve this problem? We're gonna calculate the probability distribution among all the classes for each point. and we multiply between all the points projected into the scene location, and we got the semantic fusion probability distribution, and then we take the maximum value to decide the final level of that pixel. So this is the perspective rendering. And here is the distance field. This is used to segment the to solve the problem of the occlusion. So we zoomed some areas with occlusion, and then we choose the level in this area with the depth. According to the depth information, we choose the depth, smallest depth as the level for this area to segment those two collisions. Okay, so then I'm going to show some experiment results. The data set we used is a public data set called S3DIS, and it has 6 indoor areas with 272 runes, point clouds, and each area contains about 10,000 viewpoints of 2D data, and the 2D data has its RGB information, RGB image, depth image, and also segmentation images and the camera pose information. And the input training data include 2 things. The first one is the truncated point cloud, and the second is the related 2D segmentation map. And what is the truncated point cloud? We casting the rays from the camera through the pixel to the scene, and those points on the specific viewpoints are extracted to generate the truncated point clouds. And here is the result with various proportions of data. We showed the result of 1/20, 1/12, 1/6, and 1/4. And we can say that from 1/20 to 1/6, we can get the largest improvement of the performance. And for 1/4 and 1/6, they nearly have the very similar performance. But as we know, the more data we're going to use for the training, and it means the large cost of the training. So we're going to use only the 1/6 used to be compared with the other stage of the art method. So this is the comparison with the state of the art method. And so far, as we know, our work is the first work to do the 2D supervision. And we can find that the performance of our work is comparative to most of 3D supervision method, except the SPG method. That's because in SPG it also used the contextual relationship reasoning information. And this is the qualitative results. And the first column is the original point cloud, and the second column is the results obtained via 2D supervision, and the third column is the 3D ground truth level. And finally, it's our conclusion. Our work is the first work to apply only 2D supervision for 3D point cloud segmentation, and we used the graph-based encode-decode network. And in order to get the best performance, we proposed the perspective rendering and the distance field to optimize the projection result. And we argue that 2D supervision can provide enough guidance information for the 3D point cloud segmentation. Okay, so that's all about my presentation.
Yeah, time for questions. Yeah. Yeah. Okay. Yes. Yes. No, there's one. Oh. Yeah. Okay.
Hi, thanks for the talk. So one of your main motivations was the fact that getting 3D labeled data is quite expensive. It takes a bit of time. What I was just wondering is, you say you label one of every 6 viewpoints for the 2D supervision, but what I guess I find hard to get round is it really quicker to label lots of 2D images in semantic segmentation versus labeling one point cloud?
Currently, because the data set is a public data set, so they already have the 2D ground truth. But as we know, it is always much easier to obtain the 2D image ground truth than the 3D, I think.
But that data set also has the 3D ground truth as well, though, right?
Yes, yeah, it has.
Okay, okay, that's fine. Thank you.
Yeah.
Have you tried, I'm wondering how well it generalizes to other environments, like if you try in a different room with different chair types, would it still recognize chair and table, and how well does it perform, in your opinion, on unseen scenes?
You mean to apply to the other scenes?
In other places where very different from the training data?
Currently, our research only used the data set published online.
Hi. So one of the parts of your method, when you project the points, you have some from foreground objects and some from background objects that come into the same place. And you have a method for filtering out the ones that came from behind. How effective is that? What sort of proportion does it get correct?
What do you mean?
You
mean the distance field?
Yeah.
So here we compared the result between direct projection without distance field and the method with distance field, and we can say the performance is largely improved if we apply the perspective rendering and the distance field.
Okay,
yeah,
thanks.
It has large effect of the performance.
Yeah, I have a quick question. So when you have the data set, if you have all these images, you need the camera view as well.
Yes.
Would that be, so if you can quite easily project that, 2D labeling onto 3D point clouds?
Yes.
Would that be sort of similar coverage into the information? So just want to make sure that you are pretty much using the same information as other methods you're comparing with. Is that similar?
Yeah, they use the same.
Yeah, so you can do that projection if you want.
Yeah.
Okay. Any questions from the other room?
Hello. I wonder, did you try to combine the 2D image and your 3D clouds?
You mean how to apply the 2D signal for the 3D cloud? Here we have the structure has 2 parts. We first use the GPFN to get the 3D segmentation result, and then we're gonna project the segmentation result to the 2D plane, and we're gonna calculate the loss using the 2D ground truth and the projected segmentation result.
So it means you have the label of 2D image.
Yes.
Could you show me the slides of your results, the comparison? No, yeah. So the 2D supervision is only used for RGB images.
We also use the depth image to optimize the projection result. But for the supervision, we only use the 2D signal data.
Okay, thank you.
Okay, let's have the speaker and move on to the next talk. Yeah, our fourth talk today is Orthographic Feature Transform for Monocular 3D Object Detection.
Cool. Okay. Hi. Yeah. So my name's Tom Roddick. I'm a PhD student at the University of Cambridge, and today I'm just going to talk to you about our research into 3D object detection for autonomous driving. So the challenge we're trying to face is basically, given a scene like this, we want to try and detect all the objects in the scene, so cars, pedestrians, cyclists, and annotate them with an accurate 3D bounding box around them. But the kind of like challenging thing here, and maybe kind of dangerous thing to say to a room full of computer vision researchers, but images are really bad representation, right, in some sense. Images, we have to deal with this problem of perspective projection. So things that are distant are different scales. We can't necessarily rely on the distances between objects in pixels being meaningful in meters. So basically, for this task of 3D object detection, trying to use images directly is very challenging. So what we'd ideally like to find is some sort of representation, which means we can kind of get around this limitation. Unfortunately, within autonomous driving, there's a very commonly used representation which solves exactly this problem. So basically, this involves looking at the world from a sort of top-down view. And under this space, basically, distances are meaningful. We don't have to worry about scale. It's much easier to perform like planning and motion prediction. So this is like ideally the kind of situation that we want to work with. But then the challenge is how can we go from a purely image-based representation, so no 3D information whatsoever, into this orthographic bird's eye view representation. And so that's where we introduce our orthographic feature transform. So the orthographic feature transform is basically just like a super simple algorithm which takes features in the image space and then without using any sort of depth information, transforming them into this orthographic bird's eye view representation. And so, as I say, it's super straightforward, just consists of 3 simple steps. So basically, we start by first defining a voxel grid, which is just a sort of the region that we're interested in the world space coordinates, dividing that up into a grid. And then for each voxel in that grid, we basically take the corners, project those into the image space, and that defines a region of interest which corresponds to that voxel. And this allows us to basically assign a feature vector to each voxel by basically average pooling over that corresponding image region, and then assigning the resulting feature vector back into the voxel grid. And then the final stage is, this is quite a heavyweight representation, and a lot of our kind of information is in this bird's eye view. So in order to remove the sort of vertical component of this, we basically perform a sort of collapsing operation to combine the features in the vertical dimension and get a bird's eye view. So that's basically how the algorithm works. Like the only kind of problem with this is it's very computationally expensive in terms of these pooling operations. So just to put it in context, like FasterRCN, for example, the 2D object detector, performs about 2,000 of these pooling operations in its region of interest detector. By contrast, we have to do about 460,000. So basically, we need to find a way of doing this a lot more efficiently. And so fortunately, there's like a super neat trick from the good old days of computer vision. I think like Michel mentioned it in his talk on Monday. And so these are called integral images. And basically, this is you take a image, or in this case, a feature vector, and you just take the sum up the columns and then along the rows and then down the columns. and then this generates your integral image representation. And then if you want to evaluate, say, the area of this orange region, the feature corresponding to that, you basically just need to evaluate the four corners of the region, and then divide by the area of the region, and then that gives you a feature corresponding to that region of the image. And what's really nice about this representation is, first of all, it's differentiable, and secondly, it's also independent of the size of the region. So when we're performing this projection operation, we have to deal with a very large number of different size regions, and that makes it effectively constant in the size of the regions. Okay, so that's basically how the algorithm works. So I'm just going to talk quickly about how we integrate that into a deep learning pipeline for 3D object detection. So we start kind of fairly typically by taking an image and passing it through a standard CNN front-end architecture. So we use ResNet 18. This generates a set of multi-scale feature vectors, and then of the feature maps, sorry. And then given those feature maps, we pass those through our orthographic feature transform. That generates this bird's eye view representation. Oops. That generates this bird's eye view representation. And then given that, we apply a second residual neural network, which operates on these bird's eye view features. This is kind of like the heart of our approach. So this top-down network is, we argue, what performs the 3D reasoning component of the network, which we believe is what's really crucial to this success. And then finally, we generate a set of outputs, which allow us to generate a set of 3D bounding box predictions. So those outputs consist of a confidence map, which gives a sort of coarse localization of objects in the 3D space. And then in order to refine that prediction, we need to generate a sort of offset vector, which allows us to to localize objects to smaller than the grid resolution. And then finally, we also predict the relative scale and rotation of each object. So just to show this kind of like more concretely what this representation looks like. So on the right is these confidence maps, and then on the left, I'm just visualizing them projected into the image. And so what's kind of a little bit different about how a lot of the approach that a lot of object detection architectures take is they treat this localization and detection as a classification problem. Here we're actually treating it as a regression problem. So we regress these smooth, like Gaussian heat maps. And that's actually really nice in the 3D case, because normally you'd have to do this 3D intersection over union computation to basically perform non-maximum suppression. So non-maximum suppression allows us to go from heat maps to bounding boxes. By taking this heat map approach, basically all we have to do is find local peaks in these heat maps, and that allows us to perform non-maximum suppression really quickly. Okay, so yeah, just to quickly talk about the results of our method. So I'll start by showing some qualitative results. So this is our approach evaluated on the Kitty object benchmark. And what's, I guess, the kind of, as I mentioned, the thing that makes this challenging is we're not actually using any sort of explicit knowledge of the depth of the scene whatsoever. We don't have LiDAR, we don't have stereo, so the network is having to infer the depth and kind of like geometry of these objects purely from the image data. And you can see that it's able to do that with reasonable success. Okay, so here's another example where we're comparing against what was at the time the state-of-the-art approach. So this was the Mono 3D work by Raquel Urtazan's group in Toronto. And it was maybe a little hard to kind of pick out from these videos, but one of our real strengths of this approach is that it's actually really good at detecting far-away objects. So if you look at an individual object, you can see that our detector pops up a couple of seconds or so before Mono 3D does. So that's one of the sort of advantages of our approach. Okay, so quantitatively, as I said, like at the time when we originally submitted this to the Kitty benchmark, the Kitty online benchmark, we were the leading monocular only approach. Yeah, beating by a considerable margin Mono 3D. And what was particularly exciting was that even compared to some stereo approaches, so this is 3DOP from the same group, we were able to beat them on some benchmarks. And obviously stereo is a much harder, or well, a much simpler problem because we actually do have some knowledge of the 3D structure of the scene there. Unfortunately, since then, between that and BMVC, there's been like a whole slew of like new methods which have like come up with these like super clever ways of like pushing the state of the art forwards, which is great. Yeah, so even compared to these pipelines, our method offers a much more general kind of framework that's basically, yeah, one simple, straightforward, end-to-end differentiable pipeline. And we don't take advantage of any additional training supervision. So we don't use synthetic data. We don't use any explicit depth representation, for example. Okay, so just digging into the results a bit more. So this is showing our performance as a function of depth. And as I mentioned before, like we're able to outperform Mono 3D across a wide range of depth levels. But even at the point where Mono 3D basically fails beyond about like 30 meters, we're able to still relatively reliably detect objects. So that's one of the key kind of strengths of our approach. And the kind of reason for this, we argue, is because of this top-down network. So as I mentioned, we thought this ability to reason in the 3D space rather than reasoning in the image space is extremely important because all of a sudden, like, the distances in this 3D space become meaningful, and we can actually start to take into account 3D context. So here I'm just showing a quick ablation study which shows that as you remove layers from that top-down network, the performance of the network drops until eventually you get to the point where you basically remove the whole top-down network. So at this point, the network becomes similar to something like fast RCNN, where you're just purely classifying region proposals. So this is actually kind of what you'd expect, given that we're removing layers from the network, we're reducing the capacity and therefore the performance. But what's really interesting is that if you instead use a deeper front-end network, so you take some of those parameters that you've moved from the top-down network and you stick those in the front-end network, then you actually find that the network with a deeper top-down network still performs a lot better, despite having a similar number of parameters. Okay, yes, so just to conclude then, so I've talked a lot about 3D object detection, but actually I just want to make the point that this framework is actually much more general than that and actually applies to any situation where you're actually interested in building up a kind of dense picture of what's going on in this 3D world in order to do dense prediction and planning. So here we have an example where the aim is to build a full sort of semantic map of the top-down world, not just looking at cars, but looking at road layout, etc. And this work, this OFT transform, applies equally well to this, and it's a very powerful representation, which we think is really good for any sort of like 3D reasoning tasks. So yeah, thank you very much, and yeah, any questions?
Hi, thanks a lot for the talk. I wanted to ask you something about the robustness to the characteristics of the ground plane. Actually, I think that an interesting part of this thing is that you implicitly, thanks to the convolution, you implicitly estimate the transformation from the image to the ground plane like at a local scale. You don't need to say, okay, the ground plane is planar or it's like a mathematical function, no?
Yeah.
So I've seen at the end of your videos that you had some situation like this, like you are in an uphill and then yes, exactly. So did you study quantitatively actually the advantage of this over other methods?
No. So we haven't actually done that experiment. I think it's given the size of Kitty, it's a quite difficult one to quantify. But there have been some experiments looking at sort of applying synthetic roll and yaw and pitch to these sorts of images. And yeah, as you say, because so we're not actually at any point assuming a fixed ground plane. We're basically just operating in the sort of using the z-axis of the camera. So we never actually warp to a specific ground plane. That means we expect the method to be relatively robust to that. Yeah.
Thank you.
Hey, thank you for the talk. How do you refine the predictions? Do you weight the confidence in predictions by the distance to the object, or?
So you're talking about the sort of like position offset thing? Or?
Yeah. Say you detect a car like very far, and then maybe that prediction is not very confident. But maybe you become more confident as you move closer. Do you impose any sort of?
So we're not doing any sort of temporal linking at the moment. So yeah, there's not any sort of like refinement as the positions are changing. There's a refinement in the sense that so comparable to 2D object detection architectures, where you classify an anchor bounding box, and then you apply like bounding box offsets to sort of localize it more accurately. There's that sort of refinement in place. So what you kind of expect to happen is that even if your course, the heat maps that I showed, don't exactly localize the object exactly, you hope that the offset vector will kind of like counteract that error basically. So you could do some further sort of refinement stages perhaps, but that's the idea. Yeah.
Thank you.
Any question from the other room?
So the geometry of cars are quite similar. What happens if, for example, you see a double-decker bus or a JCB or something like that?
Yeah. Okay. So I'm gonna kind of take the lazy answer and say that it's so the kiddie data set is pretty limited in the classes that it has available to train on. So in this work, I'm actually only showing card detection, and those types of objects are treated in as ignore classes. But the framework is perfectly applicable to that. So in more recent work, we've worked with the new scenes data set, which actually has a lot more of those objects. And we show that, like, given enough examples, it's actually, able to perform, perfectly well in those classes.
Yeah, one more quick question, please.
The Kitty dataset was labeled using the 3D reconstruction. So you label a 3D car bounding box, and then it gets projected on every single image. So the image you have, they have a very nice geometric consistency for the size of the bounding boxes. What would happen if you don't have it? What would happen if they're labeled manually from images? And then, quickly, can you tell me if you've chosen a focal length for your projection, or how do you do the projection?
Okay, yeah. So in this, your second question, that's probably an important point that I didn't mention, is that we're assuming we know the camera parameters for this approach, and those are actually fed in for each image. So the Kitty dataset gives you that information. So we rely on having that information. So in terms of, so you're talking about robustness to sort of inaccurate bounding boxes and stuff. I think it's hard to say. I mean, I think to the extent that any 3D object detection architecture has to deal with this problem, then I think it would be. I mean, so hopefully kind of one of the nice things is operating in this top-down space kind of builds in some robustness, because the typical approach is to take 2D boxes, and then if those 2D boxes are wrong, then your 3D prediction can be very wrong, right? Whereas because we're working purely in the 2D space, then we hope that those are more robust. But I haven't evaluated it.
Okay. Considering the time, we'll move on to the next talk. But thanks to the speaker. Okay. Yeah, the next talk is Texel at representing and classifying element-based textures by attributes.
Hello everyone, my name is Marco Godi and I'm a PhD student at the University of Verona. I'm here to talk about Texelat, representing and classifying element-based textures by attributes. This is a joint work by the University of Verona and the Sapienza University of Rome. First of all, I'm going to start with a question for you. Can these two textures be described in the same way? I think that if you look at them, you would agree with me that you would describe them differently from each other. In fact, your description would be probably something like this. The one on the left has big dots, which are dark red on a regular layout, while the one on the right has small dots, some of them red, some of them yellow, and they are on an irregular layout. If you look at current state-of-the-art attribute-based texture descriptor, you would only get a description which is like this. This is based on the work of Cipolla, deep filter banks for texture recognition, which has 47 attributes like dotted, banded, and checkered. And this is not detailed enough to distinguish textures like this. The topic of this work is a method that is able to extract an attribute-based representation which is fine-grained enough to distinguish textures like this. So, in this talk, first of all, I'm going to introduce you to the problem, and then I'm going to explain our proposed approach and the experiments that we use to validate it. And in the end, I'm going to conclude with some closing remarks. We can divide textures in two types. Stochastic textures, which are often natural textures and can be described by their statistical properties, and element-based textures, which are the focus of this work, and can be expressed as the repetition of one or more elements in the bidimensional space. The elements that are repeated are called texels for texture elements, and these kind of textures are of particular interest in industries such as fashion or design, where a fine-grained description of the properties of these textures can be useful for many applications. So this is our proposed pipeline. It is based on the explicit detection of the texels in the image, so then the computation of the attributes can be made much easier. The attributes extracted from the textures are not fixed, and the set of attributes can be easily extended based on the task that you are trying to achieve, and the attributes are interpretable, so then application can be built upon them. The first step of the pipeline is texel detection. We start from the image of a texture, and we extract for each texel a bounding box, a segmentation mask, and a classification. This is done using a mask RCNN architecture, an off-the-shelf architecture that we trained on the ELBA dataset. ELBA stands for element-based, and it is a dataset of textures that we introduce in this paper. The dataset is composed of 30,000 synthetic texture images created with a commercially available texture design software. For the creation of the images, we use different set of parameters, so we vary texel size, the spatial distribution, the number of shapes within one image, the number of colors within one image, and so on, so that we explore the wide variety of textures that can be generated by the software. For each image, we also create pixel-level annotations, such as the segmentation mask for each single texel, and a classification based on geometric shape. In this work, we consider three classes: circles, lines, and polygons. The dataset is available for download on our project page, and we use the training partition of this dataset to train the mask RCNN, so it is able to find the geometric shapes which are the texels in the images. Then the next step is the computation of individual attributes. We start from the output of the mask RCNN, which are the detections, and we cut out the part of the images where the texels are using the segmentation mask. The individual attributes are the attributes that can be computed by considering each single texel separately. So we feed the part of the image of the texel to some functions that compute the attributes. These functions can be simple algorithms, such as the computation of a color histogram or the shape orientation, and so on. So for each texel, we have an attribute vector that describes the individual properties and visual properties of the texel. So at the end of this step, we have one attribute vector for each texel, and this is the input of the following step, which is the texel grouping, in which we take all of the attribute vectors and we separate them by their class. So we have a set of circle texel descriptors, a line texel descriptor, and polygon texel descriptors, and we aggregate them into a single attribute vector by simply averaging them. If we don't have any texels of a particular class in an image, we simply use default values. Now, at the end of this step, we have for each class in the image a description that describes the average visual appearance of the texels. In the following step, we start again from the output of the mask RCNN, and we compute the layout attributes, which are the attributes that can be computed by considering the set of textile positions within the image. We separate them by class, and we feed them into some functions which, again, can be simple functions such as computation of distance properties and statistics. These attributes compose an attribute vector for each class, which describes the spatial behavior of that particular class in the image, with default values in case we don't have images for that class. In the last step, we join the 6 descriptors, the 3 individual ones and the 3 layout ones, to build a single descriptor that describes the visual appearance and the spatial layout of the texture. The attributes set that we use is not fixed. In this work, we use a set of attributes, but can be anything depending on your task. For example, these are some examples of what you can extract from our approach. You can see that local symmetry attribute, which is a layout attribute, is much higher in the first image, which is a regular checkered image, than the second image where the dots are on a random layout. If we look instead at the vertical orientation, we see that it's maximum in the third image, while it's almost not present in the first 2 images. This is the kind of properties that you can easily extract from this approach. So we perform some experiments to test our framework. The first is a detection experiment, where we test how well we can find the texels in the image. We do this on our ELBA dataset on the testing partition, and we measure standard object detection performances from the COCO dataset, such as mean average precision. What we achieve is that we have a 0.91 mean average precision, which means that almost all of the texels are found, and with a bounding box which is pretty accurate. Of course, this is synthetic data, so we test it also on real data. We take the DTD dataset, which is a dataset of 47 texture classes, such as banded, dotted, and checkered, but also marbled and other classes which are not element-based. So we choose a subset of the 12 classes, which are element-based, and we hire annotators to manually annotate with bounding boxes the texels in the image, and so that we can measure object detection performances of them. This dataset is much more challenging because we trained on synthetic data, and this is real data with surface distortions, lighting conditions, and image quality conditions. What we achieve is that we have an average precision with a threshold of 50% of 0.63, which means that we find the majority of the texels with a reasonably accurate bounding box. And we deem this enough to compute the attributes anyway on these images. So we go into the next experiment, where we perform a texture interactive search experiment based on the Witto search framework by Kristen Grauman. The idea of the Witto search framework is that you have a set of images that you want to search through, and for each image you have a description by attributes, and you can perform a search in this dataset by making relative comparisons on the attributes, which allow you to score all of the images. And using this score, you can rank the images, and hopefully, iteration by iteration, the ranking matches what you're trying to search in the dataset. So, for example, you can see in the video that you can say more or less of an attribute than a particular image to find a specific target. In the real-world setting, the target is in the mind of a user that is trying to explore the dataset. On our experiments, the target is simulated by choosing randomly an image from the dataset, and then performance measures can be extracted by seeing if we can find the target in the dataset, again, by ranking the images. So the measures that we perform are percentile rank, which is the ratio of images that are ranked below the target using the scores. And the closer we get to 1, the closer the image, the target of the search is to the first position. And we also measure search accuracy, which is we deem a texture found by the search if it falls within the first 40 images in the ranking. 40 is the maximum number of images that you can reasonably show on a web page. So if a user can find the texture in the first 40, it can be found at the texture. We set up a user study with 50 users, and we compare 5 different set of attributes. Our attributes using ground truth segmentation, and also our attributes using the segmentation provided by the mask RCNN. We also compare it with the 47 DTD attributes that I mentioned earlier, and the 6 Tamura attributes, which is another older attribute-based representation for textures. We also joined these 2 attribute-based representations to see if they perform better. What we achieve is that we have higher performance than the comparative approaches. And also, it's interesting to note that the ground truth attributes of ours are perform better than the predicted ones, meaning that the closer that we estimate the texels in the image, the closer the attributes are to human perception, since it performs better during the search. This is on the ELBA dataset, always on the testing partition. But we also tested on the EDTD dataset, which is the dataset that we extended earlier with bounding box annotations. And here, the comparative approaches work better than before, but this is a given since they are trained on the data that we are testing on. And while our approach is only trained on synthetic data and is testing on this real data, we still perform better, and we also observe here the behavior that ground truth attributes perform slightly better. So, to conclude this presentation, I will list the contribution and sum up. We introduced Texelat, which is a framework to extract an attribute-based descriptor from element-based textures. And the core idea is that we explicitly focus on finding the texels in the image. The framework can be used in many applications, and the attribute set can be easily extended based on the problem. It's just a matter of adding new functions to the computations. This is an example of another application that we have published, in which we do a retrieval application. We describe the images using our attributes, and we perform in a similarity search setting a search that we find out is more robust to perturbations such as low resolution, lighting conditions, and impulsive noise than other comparative approaches. We also introduced 2 datasets, the ELBA dataset, which is composed of 30,000 synthetic texture images with pixel-level annotations, and we extended the existing DTD dataset with the bounding box annotation for a subset of classes. The datasets are available for download on our project page, and this is the end of the presentation.
Questions?
Hi, thank you for the nice talk. So I would have a question related to the retrieval part. I think it's slide number 19, or this one, doesn't matter. So in this case, are you querying and searching in the same data set, or is the query from the synthetic data set and the gallery from the DTD data set?
In this experiment, this is the same data set. We perturb the images, and then we try to see if we can find them again in the dataset. So, for example, here the query is taken from the dataset. We perturb them with some transformations and see if we can find them in the dataset again.
So both are from the same dataset, right?
Yeah.
So have you tried something like taking a synthetic image and querying in the DTD dataset, which is a dataset of real images?
We tried, but we just have qualitative measures since we don't. I mean, we can see that they are similar, but we didn't explore quantitative measures on them. Okay. So I can give you numbers.
Okay, thank you.
Any question from the other room?
No questions.
I think considering time, we'll probably move on because we're a bit behind. Okay, thanks again. So So next talk is content color distillation for learning image translations with spatial profile loss.
Okay, so good afternoon, everyone. I'm Saqib, and I will be talking about our recent work on image translations. For those of you who don't know what translation means, it means that we want to transform an image from one domain to another, for example, from labels to full scene reconstructions, and primarily want to learn some mapping function to do that via CNNs. So predominantly nowadays, these translations are approached always by generative adversarial networks. So these GANs objective often also have a additional perceptual loss, which is based on a pre-trained classification network, and that's how they train the generator with these additional networks and loss functions. So these additional networks are both adversarial and perceptual. They are only needed to successfully drive the generator. However, despite the difficulty associated with such adversarial training, it is seldom studied if or how well we can do without it. And that's sort of our motivation for this work. And in the sense that we want to try to see if one can directly train the standard generators without the need of such extensive adversarial networks or loss functions training. Now, it is believed sort of that pixel level loss alone is not sufficient to approximate the target distribution. For example, look at this pixel level L1 loss, which is commonly used always on the top of the generator. However, if we train the generator directly with the L1 loss, it is not able to learn the one-to-many pixel mappings, color mappings in this case. In this work, we propose a different formulation of pixel level loss that is able to successfully train these generators directly. And I'm just going to talk about a little bit of intuition behind our proposal. So to understand, if you look at the patterns B and C, well, they look very different, but they both have equal number of white pixels in them. So if we compute mean absolute difference like L1 between pattern A and either of B and C, we get the same value because of the equal number of white pixels. Now, as seen, such direct pixel level comparisons are not much informative about the underlying structural changes. Instead, if we view the pixel variations along a certain direction in the image, it may form a pattern. And matching on such patterns, which we call spatial profiles, is more informative. Let's see, in our example, if we compute the distance, for example, between corresponding column vectors among pattern A or B or C, we get different values. Now, we design our loss function around these ideas, trying to view the image distribution in this induced low-dimensional pixel profile vector space. We define the loss to compute a cosine similarity between horizontal and vertical profiles over corresponding image channels. One can view this as trying to estimate or approximate the target image distribution in this spatial vector profile space. And we basically try to match the distribution in the image gradient and its different color spaces. If we view if we pose this matching in the image gradient space, then we call it the gradient profile loss, and show that it drives the shape quite well. Similarly, we define the color profile component by matching in different color spaces, RGB, YUV, and the chroma UV gradient spaces. The color profile, or the CP, so-called component, drives the color information. These two components together drive the shape and color separately, and also provide us control in how we want to use them. And I will show an example of this in the style transfer application later. So basically the loss spatial profile loss is then the sum of these GP and CP components. Now, we show its effectiveness by training the generators directly with the loss function, and for many challenging image translation problems, from image-to-image domain mappings, a single image super resolution, to a very difficult makeup style transfer application. Let's first look at the impact of gradient and color profile loss components I introduced earlier in a small ablation study to motivate how they influence or drive the shape and color separately. So here we train separately with shape, GP only, and color, CP only loss to show what they drive. We display the results at evolution of epochs during training on an image from a cityscape validation set, and also show the final output with our combined SPL on label to image problem. As you can see, the GP component drives mainly the shape because of gradients, while CP influences the color. Together, the SPL transfer the learned color properties to the shape enforced by the GP component. Now let's look at first a few quantitative and qualitative results on various applications we have considered. Here on the label to image problem, we compare the SPL loss with different state-of-the-art loss functions by training the same generator every time with different loss function. So in direct comparison to its pixel level L1 counterpart, the SPL does much better, while quite on par with, if you can see, quite on par with the adversarial GAN-based frameworks like Pix2Pix, and also quite on par with recently proposed structural perceptual loss, feature level loss component, the CX and CRN loss. And the performance is depicted by the average FC and 8 scores on the outputs by training the standard ResNet block generator, which is commonly used in the GAN-based corresponding Pix2Pix or cycle GAN-based frameworks. Next, we also show the effectiveness of this SPL loss on the single image super resolution problem. Here we trained the SR ResNet generator, which is used in the recent GAN-based framework. So our main motivation is to show that one can train the common generators, standard generators, without using adversarial loss components. So we show the results on a difficult diff2k subset 2 dataset, which have low resolution images with unknown degradations. Now, to appreciate the problem, here is a ×4 upscaled image with bicubic interpolation. And this is the output with SPL. As seen, the SPL loss manages to recover quite nicely sharp details. We naturally compare SPL with state-of-the-art in single image super resolution. While being very competitive, it is interesting to see the direct comparison with its GAN counterpart, since we basically trained the same generator used in SR GAN. While SR GAN trained this generator with adversarial and perceptual losses, we trained it directly with our SPL loss. And as you can see that not only SPL can reconstruct sharper high-resolution images, but also achieve better quantifiable results on the standard metrics. As another application, we tried it in the typical style transfer applications. So for this photorealistic makeup style transfer application, we basically propose a novel design to train single generators. We prepare a 6-channel input of source and the reference image and add the reference on the intermediate output of the generator. The generator is then trained with the SPL loss, and we use here, this is quite a nice example of showing about the control that I was talking about earlier with the 2 loss components. So for the style transfer application, we want to basically transfer the style of a reference image onto our input image. So there is no real need to really learn to generate the input image again from the data. And that's why we can basically use the gradient profile or the shape component of the loss between the generator output and the source input, just to recreate the input as it is. And then the color component of the loss can be computed between the generator output and the target, so just to transfer the color properties. And that's what we do. And our training proceeds basically by warping the reference onto the source image to have some kind of rough alignment. And while obviously the warping is never perfect, especially when there are pose changes, but the training learns to create some plausible outputs nonetheless. Now, to train and test this type of makeup style transfer, we have also collected a new data set by mining the YouTube makeup tutorial videos. And this is currently the largest data set with more than 18,000 images. And it provides images in both strong and light makeup. And it can also be used to study face recognition in the presence of makeup and face paintings. And the data set can be recreated and downloaded from our GitHub page. Now, I will just show one result out of many to motivate our design choice for makeup transfer. We compare it with state-of-the-art GAN-based approach from Adobe. And here, basically, the Chang et al. Trains 3 separate cycle GAN networks. So basically, they train 6 generators and 9 discriminators on the eyes, mouth, and face skin region separately. They then need a post-processing step to compose the 3 outputs back for the final transfer. And they trained their cycle GAN pair cycle invariant for at least 450 epochs. Whereas we trained our single standard generator with our SPL loss for only 10 epochs. And here we show the result of our super resolution makeup transfer by training the super resolution generator I showed you earlier. As seen on this difficult style, we generate better color transfer. For example, if you look at the cheek regions and the starry structure beneath the eyes. Now, because of the ease of the transfer in our design, not much post-composition is required. And that's why it opens doors for interesting online applications such as the one I'm showing you here. And it does a pretty nice job. All right, so to sum up, the spatial profile loss is a pixel level loss which can distill shape from color and is able to drive them separately for diverse image translation problems. The SPL loss can also be thought of as an effective replacement for the standard L1 loss on the generator. So when you are training your GANs, you can use, instead of L1, use this SPL loss. And to motivate this, we just trained the generator directly. Now, the central idea is to approximate the image distribution and a low-dimensional subspace spanned by this pixel profile vectors. Well, we have shown that simple vertical horizontal profiles suffice for approximating the target distribution. One can explore, obviously, more paths or orientations. For future work, for example, using any other paths could be investigated. Well, we have also tried to include the diagonal paths, but nonetheless without much qualitative improvements. That's it. Thanks. Our code and the data set is available on the GitHub page. If you have any questions, I will be happy to answer. Thank you.
Any questions? Any question from the other room?
No questions.
Yeah, okay. Microphone.
Just when you compute the gradient, do you do any high frequency filtering? Remove noise?
No filtering is done. The gradient is computed by simple pixel shifted differences of the image with itself. Yeah.
More question?
No.
Yeah, I have a quick question actually.
Yeah.
So do you so when you do this with this like gradient based whatever, do you need pixels to be aligned? For example, when you do the transfer, when you do the warping, how do you actually make sure that things are actually reasonably well aligned with the target?
Yes, we need the images to be aligned.
Okay.
And this is the case usually in such kind of image translation problems. And that's why when we do makeup transfer, we sort of align it with this warping.
Yeah, but even the warping is not perfect, but it seems that the method actually works really well.
Yeah, so for the warping, we just need the eyes and mouth regions to be aligned so that the color can be transferred on those regions, and the network learns quite effectively this thing.
Yeah. Okay, let's thank speaker. Okay, the next talk is an empirical study on leveraging scene graphs for visual question answering.
Okay. Hello. This work is done by Chen Zhang, Wei Lun, Harry Zhao, Dongxuan, and they are not able to come due to visa issues, and I'm the presenter. And they are from the Ohio State University and Cornell University. So as we know, scene understanding is always the core task in computer vision. And recent years, we have seen significant success, such as object detection, segmentation. So it motivates researchers to move on to more high-level tasks. For example, in this paper, we focused on visual question and answering. So it's like, it will be interesting if in the future, we humans can interact with machines in a more natural way. Like we ask a question and the AI gives us an answer based on the image. So just in case if you are not very familiar with VQA, so it's like it's a task that given an image and a question, the system return an answer. For example, we have this image and we ask, what is the man jumping over? And hopefully the AI return a high jump. So it's a task that require the model to perceive both visual and language information at a comprehension level. So for VQA in this 5 years, there's a lot of data sets being proposed, and they are basically in two settings. The first one is multiple choice, that we have an image question and some option as candidate answer, and the model try to rate the most likely one. And another is open-ended. We only give a pair of image and question. The model need to retrieve from a very large answer set. So there are more than 150 publications. It seems to be a very exciting problem to solve. But however, this VQA model are basically using a common pipeline that we encode the image and the text and try to fuse them. So which is general to multi-model input task. And it's not a dedicated pipeline for VQA. So, and the improvements are mostly from the beta feature or the model designs like model fusion, multi-model fusion and attention. And if we take an overlook on the performance, because they will only got a few points improvement after so many models. And a simple MLP model can even outperform such LSTM plus attention pipeline. So that makes us to rethink if there is a better pipeline more suitable for VQA. So interestingly, if you take away the visual input, question answering has been studied for a long time. Especially, they use knowledge graph to enhance a QA system. So the basic idea of knowledge graph is that you represent data as nodes and relations. So now we have more structured knowledge. So the question is, can we apply similar ideas on VQA? And actually, people in CV community have constructed so-called scene graphs. In other words, it's that we can represent objects in image as nodes in a graph, and we can annotate the relations between objects as edges. So given the question, what is man jumping over, then we look at the scene graph. We can get the answer intuitively. So we want to study if scene graph can help VQA. So in this paper, we ask, do we already have good enough scene graph for VQA? And how should we leverage them? by answering these two questions, we want to show that if using SyncGraph as input is a better pipeline for VQA. So the first question is, what SyncGraph do we have now? So they can either from human annotation, for example, the visual genome dataset, or some people have been working on a test called SyncGraph generation. That is, given the image, you automatically generate such SyncGraph. And the thing is, if you look at the state-of-the-art performance under the metric of recall, it seems that the performance are not that perfect. But so we want to validate if it's good enough for using as inputs for VQA. So here is our proposed pipeline. We have input image I and a question Q, and candidate answer C if we focus on the multiple choice setting. And we can first transform the input image to a graph G using the methods in previous slide. And the nodes and edge are actually embedding. In experiment, we'll initialize them with O embedding. And we can encode the image with CNN and encode the question and answer with O embedding and average length. Then we concatenate them together as global feature U. So now the inputs are the graph and feature vector. So now the question is, we need a model to take these inputs and predict the score. Unfortunately, recently there are some graph networks being proposed, and we introduced one of them. It's called graph networks. So it takes this graph as inputs, then you would output another graph G prime and another updated global feature U prime. So the U prime is jointly learned from the input image, question, answer, and the SyncGraph. Then so it can be used to predict the score. Okay, here let me tell you a little bit more about graph network. So basically, you will have three updates. The first one, the edge update, given the global feature, it updates the edges, then update the nodes, finally update the global feature. And the resulting graphs and global feature can be used for a downstream task like a vision QA, or even fed into another graph computational block. For more details about this network, please check our paper or their paper, please. So now let's move on to experiment. We use the popular VQA dataset visual genome. It's like we have an image, question, and several candidate answers. For SyncGraph, we want to, as the problem we want to study, so we have machine-generated SyncGraph. Neural motif is one of the state-of-the-art model of SyncGraph generation, and we also try human annotated dataset visual genome. And it even provides attributes on nodes. For example, a Haiyan is yellow and metal here. For feature, we use pre-trained feature. For images, ResNet on ImageNet. And question answer is average or embedding, and also for nodes and edges. So here is the overall result. First, we want to study if SyncGraph really helps VQA. So we first only use question and answer for the global feature. Then later we add image. So first we can see SyncGraph can help significantly, even better, with human annotation SyncGraph visual genome, and also for attributes. Next, we can see even just given SyncGraph, the green one, it can be comparable to with the image, but no graphs. So that probably means the scene graph is good enough as an image in VQA task. But does that mean we don't need image? We can see image still helps and with the same trend. And actually, it already outperformed attention benchmark model with no graph as input. So here we study on different types of question. The blue one is without graph, and the orange one is with visual genome graph as input. We can see basically graph helps on all types of question except for when, because when is probably related to more heuristic question like is it day or night. In this case, graph won't help much. So here with image feature, here are some question types that particularly helped by the scene graphs. For example, what type question and who type question is probably because the objects related to the question is often encoded as nodes in the graph. So for number question, like how many oranges are there in the image? So the model can kind of just count the number of orange nodes in the graph. That was how question can be benefit from relations. So as we mentioned, visual genome provide attributes. We can see that as we expand color, type question is benefit with attribute. Here we'll do an evaluation study that if edges in graph matters, so we remove the edge and only update on nodes, you can see that the performance drops. So actually, we can see that the drops are mostly from how and why type questions. Next, we do a sanity check. So on the left-hand side is the input graph, input scene graph. On the right-hand side is the graph output by the graph network. And we remove those edges and nodes with small L2 norm. So then we can see that it seems the graph network can capture not only objects in answer like kite, but also relations such as holding. So for conclusion, the question we asked before, do we have a high quality scene graph for VQA? The answer is yes. And machine generated scene graph is good enough, and human annotation scene graph is even better. And how do we leverage them? Graph network seems to be a good option, and because it outputs another graph, so it can help us understand the relations between objects as explainable results. So future world, we think there are some direction to make this pipeline more competitive. For example, we can enhance scene graph by adding attributes and image feature on nodes. And we can work on the graph network with current technique multi-model fusion, attention. And also we think maybe VQA is a more real-world task to evaluate the task of scene graph generation. Okay, this is the end of the talk, and thank you.
We have time for quick questions. Any question from this room? And any question from the other room?
Yeah.
Some sophisticated questions about the relationship between the objects based on their attributes and other things. But how do you think, like, what level of sophistication can be achieved using these systems? Like, for example, two people are playing some game and the scores are being kept above. Do you think it will be able to reason that who is winning the game?
You mean, can scene graph benefit games?
Yeah, like what level of sophistication can be achieved in answering the questions asked?
So we only test on VQA data sets, so it's like the one I showed you before. But for games, I think there could be a different problem because you are trying to infer many objects, and there may not be some about semantic.
Okay.
Yeah.
Okay. Thank you.
Okay, and let's thank the speaker and move on to the last talk today. Fast SCNN, Fast Semantic Segmentation Network.
Hello everyone, my name is Rudra Podel and I'm going to present to you Fast Semantic Segmentation Network, and which is done in Toshiba Research Lab in Cambridge with my collaborator. Okay, I would like to emphasize one thing. Just real-time perception is not important. I mean, it's not enough. The reason is, if you look around the most advanced autonomous system we do have now, they have quite complex system. And the perception is just a tiny part of that. Because, you see, in a complex autonomous system, let's talk about the autonomous driving, right? So what happens here? You just perceive whatever you're seeing, what is there in the scene, and where it is. These two things are important, what and where. Then you took these two informations for your planning model and your action model, right? So means when we're talking about the real-time semantic segmentations, that's not enough. That's what we're going to argue on this paper. So we're saying we really need super real fast, I mean very fast semantic segmentation network. That's the one key things. And the second thing is we want autonomous systems, means constant charging or electricity is not there. So you need to be very low compute, right? And low memory. If you're talking about the mass production, then you're talking about the really less memory, less power, and all those things. So that's the main motivation of this paper. So what is the problem right now? If you are familiar with state-of-the-art semantic segmentation networks like DeepLab or PSPNet, they are super cool. They produce really good result. I mean, their accuracy is 80–90% almost, right? Which is super good. But the drawback is they are really resource hungry. What I mean by resource hungry is three things. More compute means more floating point operations. That means more power. And you have lots of millions of parameters. Just give you a number. They have more than like almost 70 million parameters this model has, right? So this is the problem. And what is our observations? So we have quite few observations before we coming to what we proposed. I'm pretty sure some of you are familiar with this paper of Early Ropfer a group from New York University. They have shown that the early first layer of deep neural network, they learn like stroke, color detection, ages, and all those kind of things. And the higher level learns like path or higher level objects like final layers, right? So this is the one observation I would like to highlight. The second observation is, this is the paper from us in the same, this BMVC venue. So what we observe is this thing. This to know the context informations, the deeper layer is important. But if you work on these full resolutions, then it will be really slow down. So the idea is to know the context, you can downsample it and you can learn from small input images to make it more faster for efficiency reason, right? That's the, and not just only our work. In the same year, there is like bunch of work which I'm coming. And I'm very sure you guys are familiar with UNet. We know even though FCN, fully convolution neural network, they have introduced, they have shown if you have give a skip connection from like resolution of 16, 1 by 16 or 80, 1 by 8, then you can boost the performance of your system, especially in the boundary, right? Then I think UNet took to another level by adding systematically all skip connection throughout the whole, like, the downsampling things. So these are the observations. The one more observation I would like to tell you from the literature is, the ICNet, the ECCB last year, they have shown that the more, they have shown in the paper, the more you have a hierarchy, and then you can increase the accuracy, right? So I would like to point out from these observations, we draw the inspiration as well as we find out what is the drawback of these systems so that you can improve on that. That is the main motivation of this. So you see, I just show you in the first observation, one of the observations that first few layers learn the same thing, right? Why do you competing like everything separately? That's the question. The another thing is very important one. You see, you downsampling using a bilinear downsampling. Why can't we learn to downsample at the same time? Because probably the kind of bilinear downsampling doing, probably this in other kind of information is more important. So you can pull whatever more important for your context layer, right? So that is the key observation we had. And based on all these observations, we propose we propose fast SCNN. So our hypothesis was this: jointly learn the low-level feature of multi-branch network to increase the model efficiency. To prove this hypothesis, we propose learning to downsample model, which I'm going in detail in a minute. And the point of this is we want to jointly learn the low-level features. I would like to emphasize that there is maybe a wide range of observations, but very simple proposal, very simple modifications, no complexity, and we increase the performance more than twice. Sorry, in terms of speed, I mean. Okay? So let's dive into each part right, separately. So here, let's mask it out everything. Then this is the learning to downsample model. Just 3 layers. Why 3 layers? Because I'm following the tradition. Because normally we produce the output original resolutions divided by 8, right? 1 by 8. That's what we produce, right? So the idea was I want to start my context learning. I want to start my what is there in the image to learn from 1 by 8 of original resolutions. That's the intuitions. That's the idea. So what we do is just 3 layers. 3 into 3 convolutions with 2 stride. So we learn as well as downsample at the same time. Right? That's a common trick in a deep neural network anyway. It's nothing new. So these 3. So that's the idea of downsampling. It's very simple. No complexity. I would like to emphasize one more thing. Why we don't want complex things? Because if you're talking about embedded devices, the memory copy, your chip designer will not allow you anything, right? So that's the principle we have in mind when we design these systems. So it's really targeted for low resource hungry devices. So this is the second. We haven't gone away anything from the going deeper with the deep neural network. That's the trend right now, right? So we are not deviated from that. If you just mask it out this skip connection, it is a standard deep convolution neural network. Like you can think of, this is a PSP net. The only difference is we aggressively downsample so that this is still the adding few layer will give you the more efficiency. That's the key observations. Right? So still it is a deep convolution neural network. PSP net is standard PSP net. Okay? So if you just mask out this one, if you look this shortcut, because you remember in the last year paper we argued that, and we shown in evaluation studies that just with a 3 or 4 layer is enough to learn the boundary. Right? This is BMVC context net paper last year. So we following the same philosophy. So we're saying Just 3 to 4 layers is enough to learn the context and boundaries, to improve the boundaries, right? So this is here. So we just merge it very cleverly, I would say. So together, we propose you the fastest CNN. So still you see the deep path, learning the context, global context, I mean, what is there in the image. You don't need to be super smooth in the boundary, you just need to know what is there. Your blob is enough. And our shallow path is giving you the boundary details, right? So together yeah, cool. So abolishonist study for skip connection, if you don't use the skip connection, if you see the legs, it's not nice. Here is much better. If you do like this, see the pole is not here at all, so we saw that skip connection is important, right? This is a slide, I love it. Right? So this is the ECCB 2018. Same, we use the NVIDIA Titan XSP. So they use the same. And this is 57% per second. We are 123. That's the message you should take home. Right? So we are super fast. And accuracy-wise, we are just 2% drop down, not much. So this is just like progress of 3 or 4 months. Cool. So there's one more thing, and this Bisegnet, which is the closest competitor to us, is a 57. I'm repeating, I'm sorry. This is almost 6 million. We are very tiny, right? So, and accuracy-wise, we have a 3% around gap. And one more thing, I'm pretty sure you have noticed, if your image resolution size changes, then we need to redesign our network, right? That's a problem, we know all, right? But fast CNN, I would like to emphasize, it really works equally well with small resolution as well as big resolutions. I mean, if you see that this is the standard normal, very tiny, right? The very tiny, like these embedded devices, if you try this, you almost got 500 frame per second. I would like to say one more thing, community, I really would like to request, we should have a standard like frame per second measurement things, right? Everybody just don't measure this up sample. Somebody don't measure the the down sample for the multi-branch. I mean, we included everything. So there is no tweak, honestly. I'm pretty sure today in a poster I met a couple of guys. They come to me and said they reproduce in both speed and accuracy. So yeah, so cool. So that was our first contributions. And this is the second contributions. In this paper, we have observed second contribution. If you are especially in industrial settings and you want to bring your product to consumers, then normally your marketing department will give you like few hundred images. If you are lucky enough, he will give you 2,000-3,000, right? And asking the performance of PSPNet and with the ImageNet, right? So I had to go to the holiday and run my experiment. And I let it run, then we later find it out that, okay, let me explain the first thing. This blue line is just fastest CNN, right? Fastest course. And this red line is fastest. Just let's focus on these two lines, this dot and this same color, right? So the dotted line means using the ImageNet pre-training, and non-dotted line means without using the ImageNet pre-training, okay? So normally what we do, we normally run like, sorry, let's see. So normally we run a 300 epochs, right? Then you see ImageNet pre-training is doing good. Without ImageNet pre-training, you are doing bad. Up to 300-400 epochs is happening the same thing. That's why in the past, we believe that ImageNet pre-training is awesome, right? It helps. It does help, but I will come back to that question later. But in this paper, we have shown that if you train long enough, like 1,000 epochs, which is a ridiculous number to say, but you match the accuracy of ImageNet. So the key second contribution message is, if you train long enough, the key is number of gradient updates. I have written somewhere, I don't know where is it. So number of gradient updates is important. So this number of gradient updates is important. Because in ImageNet, see, 1 million images, 128 batch size, and you're training for 100 epochs. Means there are thousands of like gradient updates. Right? So if you just go close to that, it is good enough. I'm pretty sure you have now two questions raised in your head. What is the generalization, right? Come on, anyway, we all have a data set from the same domain in computer visions, and we all playing with a matrix. So I let you to decide whether it is general enough or not, but I can confirm you that we tested with the same experiment in the Cityscape data set. There is no problem in generalization, no problem at all. And these results are test and validation both results, so I can confirm you. So right, so these are the second contributions. And at the same time, too, there is RaceNet group, Gaming High, and the Facebook has come up with the exactly same idea, and they are presenting on the ICCB this year. So, like their topic is rethinking ImageNet pre-training. So it's the same thing. Yeah, I think we co-invented it at the same time. So I'll show you the result. Then where is it? So this is our video result of fast SCNN, the quality. So yeah, I mean there is a flicker. So I would like to highlight that we don't have anything like temporal coherence. We haven't used that. So I'm pretty sure if we use this, should be all right. And I'm pretty sure some of you thinking autonomous driving when coming, right? And I let you judge yourself. So, cool. Okay, maybe I will skip because we all are hungry, I guess. Yeah, you saw it there. Cool. So I would like to conclude by saying these three things. We propose fast SCNN, which is memory, computation, and power efficient. Twice fast than other state-of-the-art models. Above real time, and I think I convince you why we need above real time. And I would like to, this is equally work for small resolution as well as high resolutions. And in our second contribution, I think I convince you that ImageNet pre-training is, without ImageNet pre-training, you can get a comparable result. And the limitation is accuracy gap with the bigger model, which is with the deep lab, we are like 10% behind. And PSPNet, we are 10%, almost 10% behind. So that is the gap that is the limitation of the model, and we need to address that. And I would like to say one thing, this model is, I think I know some of the people who tested and informed me. They tried it for like depth estimation, and it's working equally well. And I'm pretty sure it will work for instance segmentations and all kind of things. And that's I left for the future work. Thank you so much for listening. And we haven't published our official code but in a public domain, if you Google it, there are lots of implementation on I found at least 4 or 5 at least today, I Google it. So in PyTorch and TensorFlow, all available. Yeah, thank you. But quality, I don't know.
An opportunity for one question from both rooms.
Hi. You showed some results on different size images. You said you didn't need to redesign the network. Was it the same network, the same train network on the 3 different sizes, or did you train it for those 3 different sizes separately?
What I mean by that is, that I haven't retrained it just because I'm not showing any results. So just for the performance, I have done nothing. Just change the input size, and I give you the number of these things. And for the accuracy, yes, we have to retrain it. Otherwise, because your filter will look for those kind of features. So yeah.
Thanks.
Let's thank all speakers for this session.